Good morning, everybody. Thank you for inviting me here. I will start this by presenting the analysis of the BOSS data that we used through a perturbative formalism known as the effective theory of large-scale structure. The results that I'm talking about are in these two papers, and they were obtained by this public code Seabird. So first of all, we all know why we're here, to continue the successes of cosmology after the CMB. We will go back to large-scale structure and potentially test much more information. The problem, of course, has always been how to get this information, because we observe a messy object in distorted coordinate. So, as a physicist, the first thing that we do is to start doing perturbation theory. And the question here is whether this is useful at all because of this complicated nonlinear physics at short scales. So in fact, the key word is short scales. Now, the cold dark matter is not a fluid, because it's basically not interacting. However, it can be recast as a gravitational fluid, and the reason that it moves very little. So dark matter only moves in the whole history of the universe about 10 megaparsec. And if you put this information into the Vlasov-Poisson hierarchy, you can actually truncate it, obtaining the usual continuity and Euler equation with interactions conserving mass and momentum. Basically, the equivalence principle is the symmetry of the problem. So the equation for dark matter are the fluid-like equation that we all know and love. However, since you start by the Vlasov hierarchy, you get in principle on the right-hand side of the Euler equation, well, also the continuity equation, but depending on the choice of variables, some short distance physics contribution. And they appear as an effective stress tensor for the long distance physics. So therefore, it is true that it is a fluid on large scales. However, it is more like an imperfect fluid, since the contribution of the stress energy tensor, the effective stress energy tensor, is sizable. Now, practically, how do you compute? Well, what you do is you take a long wavelength mode and you calculate the effect of the short distance mode in the presence of the long wavelength mode. This allows you to take into account the interaction, for instance, in Fourier space between a k long and a k short, giving a k long, and also the fact that two short modes will give a k long. Now, with this formalism, you know that large scales are perturbative, basically in this parameter, delta rho over rho, which is the usual one of Eulerian formalism. What you get is something proportional to the long distance field. An important caveat is that you actually get an integral over the fluid trajectory. And the reason is that time scales cannot really be separated. Everything happens on time scales of order inverse Hubble. So although short distance scales can actually be separated, time scales cannot. However, you can also do perturbation theory here, because now you know that this integral has to be done along the fluid trajectory, and the fluid trajectory is basically x plus vt, roughly speaking, and therefore you will expand that too. And that's how you will get the final expression that will depend only on the long distance field in a way that's compatible per the effective theory mantra with the symmetry of the problem. So basically, here you see an effective pressure, something that's a speed of sound term, and then you get terms proportional, well, to the squares of these things, to gradients over the K and L distance, to second derivative of the potential, since the potential and its gradients are not really observable, and so on. So the problem now also is how many terms to keep. Well, this is a bit more complicated since it is true that in a power law universe, delta rho over rho scales cleanly as K over K and L, but here we are not like in quantum field theory, so there are no analyticity properties and so on that that allows us to immediately classify the terms. However, we know that in a short range of wave number, the power spectrum can be approximated as a power law, and so we can actually do fairly adequate estimation about how many terms to keep. Now, so far, I've given you the essence of the method, and so far, I basically only talked about dark matter, cold dark matter. However, as I said in the beginning, as you all know, we observe galaxies in Reggie space. So one can do step by step with the same perturbative framework in mind and examine this effect. So baryons. So baryons are not really more complicated. It's just that in the end you will get an effective theory with two fluids with similar nonlinear scales. That's because on long distances, basically baryons follow the same potential wells. Then galaxies. So galaxies are objects that depend actually on UV physics, very complicated physics. However, the long modes of their count density field can only depend on the large wavelength fluctuations of dark matter and baryon fields. So here it is important to include all terms allowed by the symmetries. So we get a bunch of bias coefficients, and what's important is to get a complete basis, which in principle allows, which make us tell that we are not missing any effect. And finally, there is the Reggie space. So the Reggie space is nothing but a change of coordinates. So we all know how to make change of coordinates in general relativity or even Galilean physics. The problem is that it is still dependent because of the local velocity field. So the only thing is that it will bring us counter terms, additional, due to product of fields at the same point, but basically it doesn't introduce any different problems if it's treated perturbatively. One finally important effect that I need to stress is that the Eulerian perturbation theory converges very slowly because of the effect of infrared displacement, which affect the BAO peak in real space. So there is this BAO scale in the universe, but since there are modes of the velocity that will move things around, this BAO peak is less pronounced and more wide. So this effect actually can be taken into account in a non-perturbative manner. So this is the magnitude of the effect. It is about 1% of the monopole and like up to 5% on the quadrupole. And the formula that one gets is basically an integral or a matrix multiplication, if you want, of something that depends both on K and on S, real space coordinates, times the non-resummed correlation function. Now, several approximations have been made to this formula, but we choose to implement the full formula in our code. This is, I have to say, numerically subtle, and it is the time bottleneck. However, we have succeeded on making the code very fast using different tricks, like FFT log and summing and subtracting terms in order to make computation easier. Then just talk to me if you're interested. So finally, let's put it all together, and we have the halo power spectrum in Ricci space. You get the term, the linear term, something like the P22 term, something like the P13 term, and then you have counter terms which depend on the long distance power spectrum, and then you get these epsilon terms, which are noise terms, which, as you see, one is the short noise, and they just describe the effect of two short distance physics modes that go to create a long distance physics mode. So they will not depend on the long distance power spectrum. Okay. So far, this is the theoretical model, okay? And we are confident now that this theoretical model up to a Kmax, some Kmax, up to some precision, theoretical precision, will capture all the effects on lab scales. So now we go and we build up a likelihood with this model. And luckily, there are a few tricks that we will employ in order to make things faster. So one is the exact marginalization. So overall, there will be 10 effective theory parameters, like 4 biases, 3 non-stochastic counter terms, 3 stochastic counter terms. But some of these appear linearly in the power spectrum. So if you have a Gaussian likelihood, you can marginalize exactly over them. And then we end up just with 2. Because actually the 3 of them, we will see that they do not improve the fit, and therefore we just put them to 0. This is just a choice of the model. We could as well fit them, but they are not giving us any information, just slowing us down. And finally, the window function, which usually is applied to the power spectrum, this is now difficult because since this is a perturbative description, in the UV you get these power laws, and so it's better to do a convolution of the window in Fourier space, but we choose to just mask the covariance once and for all. So this is something that makes the code also very, very fast. So now let's go to the actual data analysis. And here we do a first step, which we think it is very important, which is the check on simulations. Since this formalism is new, and it actually now predicts its own failure at some point, we want to know which is the Kmax to which we can trust our theory, and also to estimate the systematic theory error by using a big volume simulation of which we know the cosmology. And finally, also to check the validity of the model. As I already mentioned, for instance, we realize here that 3 parameters of these 10 do not play a role. And so for the moment, they are dropped. And until we get more precise data, we can drop these parameters. So finally, we go to the data. We select the physically motivated priors, and actually on the cosmological parameters, we will do like a totally uninformative prior. and physically motivated priors on the bias such that each term in the expansion is still perturbative. So I will present result for simplicity for 3 parameters and then for the full new lambda CDM. Okay, let me start by showing you how we compute the Kmax. So we use challenge boxes from SDSS. They are good quality and body simulation populated with 4 different HODs. And we check that the theory systematic, which is this second line, is actually very small. And we choose to stop at this 0.2. This is a 5th independent simulation. We have very similar results. And actually then, after deciding where to stop, here we show that we basically recover the right cosmology. And we also demonstrate that the simulations have differed by the bias, which is the HOD model. Now, the generacies are broken. Also, another check is that the best fit is still consistent with perturbative. So at 0.2, the P1 loop to P11 is about 10%, and we can estimate that the P22 loop over P11 is about 1%. So here we actually have some sort of estimate for the theoretical errors that we will need to compare to the data, to the data error. Finally, we also check observational effects such as window function, redshift selection, and fiber collision on these patchy mocks, which employ approximate gravity solvers. And we also here find a negligible systematic error. So after all of this, we stop for a moment and we ask, so how is it possible to actually measure these things? So the reason, if one does a back of the envelope estimate, is roughly speaking that, for instance, the BAO scale scales as omega m over h to the 4th, and the BAO amplitude, if one fixes the ratio of baryons to cold dark matter, scales as omega m h square. Plus, the linear monopole and quadrupole amplitudes have different scalings. They differ by f. So now we can actually, if you take these 4 points of information, we solve for the 4 variables. And then we predict anti-correlation, and then the anti-correlation between omega m and h is very, very mild. So finally, let's go to the data. So we can apply the model to the BOSS data. The best fit has a good p-value, roughly 0.2, and the residuals do not look problematic. So this is what we get for the 3 parameters for CMAS and GC. So the result of AS. So AS for this particular data set is lower than the Planck value. We get an omega m measurement which is similar to Planck, and also a fairly precise measurement of H. Then we also analyze the low Z NGC sample, which has larger error bars, and we check the consistency of subsamples, NGC, SGC, and the low Z NGC, and finally we put them together. And we check that omega m is as good as Planck and H0 as good as supernova, and can do better. And can do better since we can actually now go to new lambda CDM and impose a different priors, because these results are made with a priors that fixes the ratio of baryons to cold dark matter. However, we can actually relax this. So I skip all these tests on simulation. As you see, they tell us that even with this enhanced parameter space, we are fine. And I present you the final result. that are done without CMB information, there is a wide prior on NS and a BBN prior on omega baryon. The only thing is we put a prior less than 0.9 electron volt on the neutrino mass. So these are great results. It has a small error on Hubble determination of NS alone to 5%. We still have a wide interval for the sum over mass of neutrinos, which can be broken down. And this is what we get by combining all three data sets. Okay, let me conclude. One important point is that we have a new independent H0 measurement with 2% precision, which comes from a global fit. And we notice that this error is larger if we put the prior on FBC instead of omega B at the cost of a slightly increasing error in omega B. So this is done by a public code, which is available here, and please ask me if you want more information about that. So what next? Well, we have some lists, both from the theory side and the observational side of possible project and suggestions for the future. So for instance, from observational side, we ask accurate measurement of higher endpoint function and also, for instance, of the hexadecapole, maybe get a better feeling of these EFT parameters from simulation and address now the observational systematic errors, since now the precision is so high that we have to care about accuracy. So, summary. Somewhat surprisingly, contrary to what many people in the community, in part also me, had felt before, we have a first determination of actual new lambda CDM parameters from the full power spectrum alone, without additional information. And we can actually get a major qualitative and quantitative improvement. And now LSS, I would say, has entered completely the era of precision cosmology, hopefully at the level of the CM. Thank you.
Time for a few questions.
Yes.
Excuse me. Perhaps a slide went by too fast I misread, but it looked like your H0 for the CMAS only analysis was 72. Is that right? Did I read that right?
For the CMAS NGC, yes. Here, you mean? Yes. Yeah, but the error is much wider because this is a different prior on FBC, which is the ratio of omega B over omega C. So as you see, the error here is like 3.2. So, and also, let me stress that this particular sample, for instance, has a very low AS. So this particular sample, yes, it pushes things in the different direction. However, it's mostly compatible because of the different prior. Yes.
The fit is still good.
Well, yes, the fit is still good. I mean, it's a p-value is about between 0.2, 0.3. Now I forgot the exact number. So, but you know, it is still good. I mean, within the error bars, the p-value is not terrible. Yes. Yes.
So about the FB prior, is this you fix the baryon fraction? Or it's just it's a flat prior?
We explore two different priors, as I said. So in this first analysis, because we do a grid, we fix the ratio of baryons to cold dark matter, basically to the Planck value. I mean, the error is so negligible that we just put a delta function on that. However,
The error from Planck.
Yes. No. We assume a prior information. I mean, this is the definition of prior information. Right? We take this from Planck. However, then we completely relax this, And we do here we do we remove the prior on that, and we have omega B, which is not shown here since it has the BBN prior, and it's it's basically just a prior. So I don't show it, otherwise you don't see the interesting parameters. Yes. So we explore also the effect of different prior. And as you see, with this prior now, the error on H goes down. At the expense, there is a bit trade-off between the error on H and omega N. Yeah.
Let's thank Guido again.
Thank you.
All right, next up we have Alex telling us about a joint analysis of power spectrum and bispectrum.
Right. Good morning, everybody. So yeah, my name is Alex. I'm coming from Durham University. And yeah, first of all, I would like to thank the organizers for giving me the chance to present some of my recent work here. And this is work I've done together with Roman Scocchi-Merrow, Rob Smith, Martin Croce, and Ariel. And this work was focused on improving the modeling of the bispectrum, in particular for galaxy bias, so that we can do a robust joint analysis of the bispectrum together with the power spectrum. And since we've already heard a lot about the power spectrum in Guido's talk, here's just a brief introduction to the bispectrum. And while the power spectrum is it's defined as a correlation between two density modes, the bispectrum is a correlation of three density modes at wave vectors K1, K2, and K3, which have to form a closed triangle. And in the absence of any statistical anisotropies, the bispectrum actually only depends on the magnitudes of these three wave vectors, so that it's a function of three variables only. And so this dependence on these extra wave modes allows the bispectrum to probe more complex shapes in the cosmic web. And to demonstrate that, this is I'm plotting here the configuration dependence of the bispectrum. And what I'm showing here is actually the reduced bispectrum Q, which is the ratio of the bispectrum divided by products of the power spectrum. And then I've integrated this reduced bispectrum over one of the triangle sides while keeping the ratio to the other two triangle sides constant. And this is what's plotted here on the X and Y axis. So here we got the ratio of K3 over K1, and here the ratio of K2 over K1. So that up here in the top right corner, you have equilateral triangle configurations, top left corner, squeeze configurations, and down here are the folded ones. Right, and so this measurement was done from a simulation using Gaussian initial conditions. So what you actually see here is the gravitationally induced bispectrum. And a very prominent feature in here is that we get a very strong signal for these collinear types of triangles. And this is really due to the fact that the large scale structure is very filamentary. And this is what the bispectrum picks up. And that's what I mean by this shape dependence. Right, so why do I think the bispectrum is going to be a very, very important for maximizing the potential of all the upcoming galaxy surveys? We have a bunch of reasons. First of all, being able to probe these extra shapes means that there's going to be extra information in the bispectrum, information that we cannot extract from the power spectrum on its own. So this is going to help improve constraints on all of the cosmological parameters that we're interested in. And then a second important, very important reason is that combination of 2- and 3-point statistics is going to help us to break degeneracies in our parameter space. A very prominent degeneracy that we face is the degeneracy between the growth rate f and the amplitude of fluctuation sigma 8, which in the power spectrum just depends on f times sigma 8 squared. So if we just measure the power spectrum, we cannot disentangle these two parameters. But the bispectrum depends slightly differently on these two parameters. So putting them together allows us to get constraints on them separately. And there has been like a fairly recent Fisher forecast on what we can do, for example, with DESI on the growth rate. And this has shown that the bispectrum is going to improve the growth rate by factors 2 to 3. So that corresponds to like an increase of volume factor 4 to 9. So that's really an immense improvement that we shouldn't just disregard. And another reason that, I don't know, didn't fit here on the slide anymore, but I think it's equally important, is that the bispectrum is also allowing us to trace prime model non-causalities. Right? So it's another reason. Okay, but for such a program to succeed, of course, we need models that are capable of, that control various effects in the galaxy density. And this involves the nonlinear evolution of the matter density. It has to account for redshift space distortions and galaxy bias. And if we constrain ourselves to fairly large scales, then we can attempt to model all of these effects using perturbation theory. And the spirit of perturbation theory is to expand our observables, like the power spectrum, bispectrum, in terms of the linear matter density field, right, delta 1. And, or well, cross correlations, let's say cross correlations between delta 1 and higher order density fields delta n, which are, again, related to the linear density by the nth power. So for example, in the power case of the power spectrum at leading order, or also called tree level, we have a correlation of just the linear density field. Then the next to leading order, or one loop, we have correlations between the third order and linear one, and correlation of 2 second order fields. Whereas for the bispectrum, assuming we have still Gaussian initial conditions, the leading order term is given by a correlation between the second order and 2 linear fields, right? And this is really the state of the art currently from past analyses that have been done, for example, by the Boss team. So you can see that, that these analyses, they treat the power spectrum and bispectrum slightly different footing, in that it ignores the one loop contributions to the bispectrum. And this is going to limit the range of scales where we can carry out this joint analysis. And well, so to include these one loop terms, I've written this down here, you have to go up to 4th order in the linear matter density to capture all these effects. And that's what I'm going to focus on next, in particular for galaxy bias. So if we want to go up to this 4th order, then we have to expand the galaxy density in terms of all the matter contributions. And the question is then, of course, what are these different contributions? And I think in the last 10 years, roughly, there have been many developments in the field that tell us exactly what are the types of terms that we should write down here on the right-hand side. And I don't want to go into too much detail here, but I think you can categorize these types of contributions into three groups. The first one is very large-scale gravitational effects. And the second one come in at, say, like roughly the scale of the halos. They're also called, what I'm writing down here, higher derivative terms. And finally, some stochastic contributions that model the very small scale effects on galaxy formation. And like a little bit more detail. So in this first group, we have all terms that get generated by spherical collapse and tidal fields. So these involve like our the usual terms. For example, on very large scales, we have that the galaxy density depends on the matter density times some unknown linear bias coefficient B1. Then at second order, we get the density squared and something related to the tidal field. I call this G2 here, times the tidal bias parameter gamma 2. And then at third order, we get a bunch of extra terms, and similarly at 4th order. The details here are not so relevant, but just writing this down here. But what I want to highlight is for the one loop power spectrum, there are only 4 terms that actually are relevant, and these are the first and second order terms and one of the third order terms. Whereas for the one loop bispectrum, all of these terms that I've written down here are important, So in total, they are, going up to third order 7 free bias parameters. And if you also take into account these fourth order terms, 11. I'm writing this here in brackets because I'm going to fix these fourth order bias parameters, and I'll come back to that in a bit, what and how we actually fix those parameters. And then these stochastic contributions, as I was saying, they model the small scale effect on galaxy formation, and they are mostly uncorrelated with the large scale fields. So what they actually look like is noise. So they produce corrections to your Poissonian shot noise. In case of the power spectrum, this is then just modeled as a free constant and not. And for the bispectrum, this looks exactly like the Poissonian shot noise, but with 2 free parameters, which I call here epsilon naught and eta naught. Okay, so in total, for the power spectrum, you will get 5 free parameters. And for the bispectrum, using the 7 + 2, 9 free parameters that you have to include in your model. And I'm skipping now a bunch of details of how we compute this one loop bispectrum. So if you're interested in that, just please come find me afterwards. I'm happy to give a bit more detail, just in a private chat. Right, but what I want to tell you now about is what are the results from fitting this model to mock galaxy data. And just very briefly, we assume a Gaussian likelihood for this, and with X being the data that we've measured from these mock catalogs, mu is the model, including all these bias terms that I've shown you on the last slide. And for the bispectrum, we also have to include some binning correction, some integral over the bispectrum model that turns out to be very, very important. And finally, the covariance matrix. And this covariance matrix is measured from our simulations, and we assume a diagonal matrix, not a Gaussian covariance matrix, but diagonal, where the diagonal entries are the variance measured directly from the mocks. And this is okay to do because for these mock catalogs that we use, they are very shot noise dominated. That means that all the off-diagonal elements in the covariance matrix are suppressed compared to the diagonal. Okay, so a little bit more detail on the simulations that we use. So most of the data that I'm going to show is based on these Minerva simulations, which is a set of 100 periodic boxes, each with the volume of 1.5 gigapascal cubed. And they were populated with HOD galaxies to match roughly the CMAS number density. And out to a Kmax of 0.25, we then measure like 60 bins in the power spectrum and about 2,600 bins in the bispectrum. And then I'm going to focus on 3 different modeling options for the bispectrum. So one is inspired by the model that was used in the BOSS analysis. And in there, they've used not the full one loop term for the galaxy bispectrum, but they use the one loop term for the meta contribution only. Then they use tree-level bias, and they fix a bunch of these bias parameters, all these tidal parameters, and make some assumptions about the shot noise as well. So in total, they end up with 3 free parameters. Then I'm going to show you some results based on the full tree-level result, which has 5 free parameters, and then the full one loop model. Right, so let's have a look at the data first. And this is very similar to the plot I was showing you before, now in 3 different bins of K. So this is integrated from, over one of the triangle slides from 0.1 to 0.12. This is 0.14 to 6, and then slightly higher on the right. And these are the residuals using the one loop, well, not the one loop, but the BOSS model for the bispectrum. Right, so you can see that if you go to higher scales, a higher Kmax, that the model starts to break down in the top right here, so for equilateral triangles. And now for the one loop model, this is how it looks like. So these residuals are all fairly small. And I think what might be interesting to see is that if you look at the impact or the contribution from the galaxy bias loops, right? How important are they? This is what's showing here now. So this goes up from 0 to about 20% with respect to the total bispectrum. And you can see that in particular, it's the equilateral triangle configurations where the loop contributions are important. So that's in line with what we were seeing before, right? And they roughly become important at scales of 0.15 inverse megaparsec. 5 minutes, okay. Got to speed up a little bit. Right, so because these residuals weren't as good for the Boss model, this also has impacts on the recovered bias parameters. And so I'm plotting here. This is the Boss model compared to the one loop model here on the right. Showing here in this column, this is the linear bias, where we have a true, let's say, correct measurement from the cross galaxy matter power spectrum. So this gives us a very precise value that we can compare our fits to. And you can see that, well, here in gray, it's the power spectrum, blue, the bispectrum, and green is the combination of the two. And you can see that these contours don't, overlap very well. It seems like the power spectrum bispectrum are fairly inconsistent, whereas this inconsistency goes away if we use the full one loop model on the right. Now, one thing I'd like to talk about is, or maybe one concern that you might have is, if we use this one model, we have so many more bias parameters, right? So there's a lot of freedom in the model, and that might reduce our constraining power, obviously, on the parameters that we're actually interested in. And so now I was interested to see if there are ways of fixing some of these bias parameters. And so there's, for example, these time evolution relations that mean when you start off with some even non-zero bias in the very beginning, if you evolve the field gravitationally, you will automatically produce a contribution at late times. And for example, for the second order tidal bias parameter, it looks like this. So this is the gamma 2L, this is the initial tidal field bias, and at late times you get this extra contribution that depends on the value of the linear bias parameter. And similarly, at third order, you get very similar relations that depend on B1 or also gamma 2, and so on. And the Lagrangian coevolution relations are when we say at initial times, these bias parameters were all 0. But at late times, they are given in terms of these relations, right? And now I'm going to use these relations. So I make these parameters, I don't set them to 0, but I make them depend on some of the lower order bias parameters. And a second set of relations you can get from the peak background split. And these allow us, for example, to get relations for the local bias parameters B, B1, B2, B2, B3. And there have been measurements from PT1 Lazaras a few years ago that produced relations, fitted relations for B2 and B3 as a function of B1. And I'm going to use these relations now in these parameter fits to see if we can still get unbiased constraints on B1. Right, and that's what I show here. So this is the full parameter space for the one loop bispectrum. The first column again is the linear bias, and again is the true value. So this is what we should compare to. And right now, right, okay. These other vertical lines, they are either the PBS, the peak background split relations, or the coevolution relations. And right, so this happens when you start fixing some of these parameters in terms of these relations. Okay, so light blue is just fixing 2 of the third order parameters, then blue another one, and finally green is fixing even B2, one of the second order parameters. And you see that while doing this, the constraint on B1 doesn't get any more bias. So you still recover the true correct value. And even if you look at the combination of the power spectrum and bispectrum, this still remains true. Okay, so final set of slides that I'm going to show is now some model comparison, because of course there's a trade-off, right? I mean, if we reduce this parameter space, then our model might break down earlier, but it might have a higher constraining power. So you know, what model should we use and up to which scales, right? What's the best option here? And that's what I'm trying to attempt to show in this plot here. And I'm going to quantify this in terms of what I call this figure of bias, which quantifies the difference between the posterior mean. In this case, I'm going to use the linear bias parameter as a diagnostic, and its fiducial value, right? And this is the parameter covariance matrix extracted from the posteriors as well. So the higher the figure of bias, the worse, well, the less we should trust this model. Then the other thing I'm going to plot is here the figure of merit. This just gives us the constraining power on the linear bias value. And then finally here I have the chi-square with its 68 and 95% confidence levels. Okay, and I'm going to show this for the CMS, you know, the Minerva simulation that I had before, but now scaled to a different effective volume. So this is now 6 gigaparsec cubed. Then I have something similar for low Z and the main galaxy sample as well. And okay, I'm about to finish off just showing this set of slides. So here, this is what you get for the full tree-level bispectrum, which you can see does reasonably well actually, particularly for CMAS, fails about 0.616, and then it goes to consecutively smaller Kmax values as you would expect, because the redshift of these sample is decreasing from the left to the right of this slide. And right, so I plot these values, so I discard this model if the combination of the figure of bias and the chi-square becomes too large. So this is somewhat arbitrary, but it just allows us to make a comparison of these models. And this is how it looks like for the one loop bispectrum, with some of these modeling options that I was presenting before. So the dotted line is all free. Then some of these bias parameters fixed, and the dotted line here, this is with most 4 parameters fixed. And you can see, first of all, that using this one model, we are both able to push further to larger Kmax values, but also achieving better constraining power on this parameter. And something very similar is true if you look at the combination of P plus B. And last slide, if you look at a combination, well, now also varying sigma 8, so the amplitude of fluctuations, where now figure of bias and figure of merit are based on the combination of these two parameters. So again, we are able to achieve big improvements by looking at the one loop galaxy bispectrum. Oh yeah, and what I should also say, by looking at these best Kmax values that we can achieve here, we get about a 6 times improvement in the error of sigma 8 by adding the bispectrum to the power spectrum. Okay, so that's my talk. So just this is what I think you should pretty take away from this. So consistent treatment of the power spectrum bispectrum is necessary to recover unbiased constraints on the linear bias and sigma 8. And this means that we have to take into account loops in the bias expansion beyond roughly scales of 0.1 inverse megaparsec. Then I've shown you that coevolution and PBS relations can help to reduce quickly inflating parameter space without biasing our results. And even after marginalization of a galaxy bias, there's still significant constraining power in the bispectrum. So with that, thanks very much.
We have time for just a few questions.
I don't understand this argument that the argument of the covariance is diagonal. I mean, combining all the measurements together, then the other argument becomes important.
Yes, well, I mean, it's just compared to, so if you look at this covariance matrix, right, from the measurements, then all the off-diagonal elements, they are consistent with noise in this measurement, compared to the value of this.
That's certainly not true for the power spectrum. It's even less true for the bias spectrum, right? I mean, maybe that's true because we have enough summations.
Yeah. Well, I agree that this is an ideal case. This is if you were to take the full covariance matrix, I'm sure these improvements that I was talking about are going to decrease. No doubt about that. Well, we are limited to this case, of course, because we don't have enough simulations to measure full covariance metrics. But also, this approximation isn't as bad, I think, as it sounds.
Do you have argument that all the improvements that you're carving will not go to zero? Do you have proof for that?
Well, no, I can't. I don't know how the exactly how the off-diagonal elements, if you have full covariance metrics, are going to impact this quantitatively. But well, yeah, I don't know. Sorry, I'm quite sure how to answer that question now. Yeah.
So when I looked at this using the Keyless simulations, when you ignore the off-diagonal terms, it ends up being like 20–30% effect for the bispectrum form.
Right.
This is the halo bispectrum without marginalizing over 5 parameters.
Okay.
So I don't think it goes to 0.
This is for like what range of scales?
This was, I looked at K at 0.2,
yeah,
K max 0.5.
Okay. Yeah. Okay, thanks.
Okay, if there's no further questions, let's thank the speaker again. Right, our last speaker before the coffee break is Stephen Chen.
What do you think? Does it change slide by going? I press the change slide. Oh, okay. Hello, everybody. I'm going to be talking about. Well, I'm Stephen Chen. I'm a grad student here at Berkeley, and I'm going to be talking about modeling RSD using LPT, or a speedy perspective of this, at least. And you got me. I didn't mean speeds. I meant velocities. So I suppose I could be speaking too quickly, so it could be speedy as well. If somebody can come up with a better title that actually involves the word velocities and not speeds, please tell me. I think it'd be much catchier. I thought something about velociraptors might work, but maybe not. Okay, so anyways, the outline of the talk will be as follows. I'll talk about the link between redshift space distortions and velocities, and how we can use velocity statistics measured from simulations to look at the convergence of various expansions of velocity of RSD. After I do this, I'll talk about modeling these velocity statistics and Lagrangian perturbation theory. In particular, I'll talk about modeling the zeroth, first, and second velocity moments. And then finally, I'll talk about how both of these prongs can be combined to model the power spectrum in redshift space and LPT. Okay, so to begin, I'm surprised this slide hasn't come up yet, so I'll talk about it. But so as most of you probably know, or probably all of you probably know, the effect of redshift space distortions is to take the observed position from the true position x to x plus the line of sight velocity in Hubble units. On large scales, this has the effect of enhancing clustering along the line of sight. And on small scales, we get the effect where the random velocities dominate and structure along the line of sight is suppressed. And the interesting thing is that this effect introduces a sort of independent scale on top of the nonlinear scale in perturbation theory, which is set by the size or by the magnitude of the random velocities at small scales. And for typical halos, this effect is on the order of megaparsecs, and so it's a sort of a comparable scale to where perturbation theory itself, even in real space, breaks down. And so mathematically, the effect looks as follows: the power spectrum in redshift space is equal to, it's given roughly by assigning a sort of additional phase between two pairs of points, which is given by the pairwise velocity difference, and then if you Fourier transform it as you would the correlation function in real space. And so when you take this, and so all the models of redshift space distortions, at least perturbative models, basically amount to how you deal with this exponential phase, right? And so in some ways, the most straightforward thing to do is to expand the exponential term by term. And when you do this, you get what is called the distribution function approach. where basically your power spectrum is given by order by powers of the velocity moments in real space. And what I mean by this is that when you expand this, when you expand this exponential, you get a bunch of expectation values that are the density weighted pairwise velocity moments. And after you Fourier transform these and you sum them up, you get the power spectrum in redshift space. Of course, you can also choose to not do this entirely, and you can really just collect. You can also just expand this exponential and collect terms order by order without thinking about velocities at all. And this is what Guido was talking about earlier, for example. Right, and an important thing to remember is that because we're looking at the sort of line of sight velocity, in some sense, this expansion, because the only components of this that are relevant are the sort of line of sight components, or in some sense, there's an expansion in the parallel component of the wave vector, which is given by k times this angle mu. All right, mu is the angle. Well, mu is the cosine of the line of sight angle. Oh, well, I forgot about that. Right. But of course, doing the Taylor series is not the only way you can expand exponentials. And for example, one other way you can do this is by using the cumulant theorem to instead write the redshift space power spectrum as 1 plus the dimensionless redshift space power spectrum as 1 plus the spectrum in real space times a series of cumulants. And these cumulants can be computed, though they're a bit harder to physically interpret. And these cumulants take the form of the transformed Fourier space velocity moments divided by this prefactor. And there are many other options you can do as well. I keep on forgetting about these. Okay, so what we can do is we can measure these guys, these velocity statistics from simulations, measure the redshift space power spectrum from simulations, and measure the real space power spectrum from some simulations, and see how each of these expansions converge. And so here, is there a way to make the top thing go away? Oh, okay. Is obscuring a little bit the legend. So I'll tell you that each of these lines is what I'm showing here are statistics computed from the redshift space power spectrum wedges. And so the blue, orange, green, red, and purple curves are given by, no? No. Okay. Our mu equals 0.1, 0.3, 0.5, 0.7, and 0.9. The top is just the plain power spectrum wedges, k times, well, multiplied by k for ease of presentation. The second thing is this ratio here of this guy divided by that guy, which, so in some sense, we're isolating out only the velocity statistics. And the final one is the error of each expansion. So let me, because you can't see this, let me go through each of these with a bit more care. So this side is using the distribution function formalism. And so you see the dotted line, which is hidden here, the dotted line is if I only keep up to the second order in velocities. The solid line is like if I go to the third order, and the dashed line is if I go to the fourth. And so you see, especially at high mu, there's a great improvement from going from n equals 2 to n equals 3. It's worth noting that even that for small angles, even n equals 2 is very good if I only keep up to the second moment of velocities. But if I go to n equals 3, if I go from the third moment to then add the fourth moment, something puzzling happens. And this is, well, something kind of puzzling happens. And this is that it doesn't actually look like these expansions improve. And while it doesn't look like they improve, you can see that actually what happens is that for small angles in small k, you get closer and closer. You actually do get asymptotically closer to the redshift space power spectrum. But once you go to large angles, this effect goes away. And this is because once you go from n equals 3 to n equals 4, your expansion becomes dominated by the random velocities and the convergence is not. And so we can see here is for the distribution function approach, what we really need to do in some sense is to model accurately up to the third velocity moment. And unfortunately, the other interesting thing that one gets from this is that both of these formalisms for expanding in velocities are very similar. They produce essentially identical results. Okay. So now that we've done this, we can move on to discuss how to model these statistics using Lagrange perturbation theory. And so the ingredients for this modeling, as has already been mentioned by the two previous speakers, is the long and short modes of both densities and velocities. And so to begin, let me first talk about how one models galaxy bias in Lagrange perturbation theory. So we have is that the initial galaxy over density is given first by the response of the galaxy field to the large scale structure, which is given by the first and second order and so on Lagrangian biases. And then we have these sort of finite size or sort of effective corrections due to the, in this case, the finite size of halos and a response to the environment. And finally, we have stochastic contributions due to modes below the halo scale that we do not model, and that are independent of the large scale structure. And so we can think of the velocity very similarly. The velocity is given by the long modes, the contribution of the long modes given by LPT, and then there are effective contributions. And then finally, we also have stochastic velocities, and unlike for the densities where the stochastic terms are some scalar modes, here we might really expect for the displacements, I guess I should have said displacements. For displacement and velocities, the stochastic contributions will be very important because, as we saw from the data, they're beginning to dominate. They're beginning to dominate redshift space distortions at even at rather perturbative scales. And we can translate from these Lagrangian displacements to velocities just simply by taking a derivative. And because we do not, in principle, know the time dependence of the effective portion of the stochastic modes, these translate to being free parameters. So the stochastic modes are especially interesting to us in redshift space. For the densities, this looks roughly as been mentioned before, like a noise term, but the stochastic modes, the correlation between the densities and the velocities and the autocorrelation of the velocities gives an additional vector structure that can give things like fingers of God. And once we combine all these things, a unique feature of LPT as compared to the Eulerian treatment is that what you do then, once we have all these ingredients, is you take the initial Lagrangian galaxy density and advect into their final position using this displacement that we've computed. So, okay, so how do we measure these? The gist is to use LPT to predict this statistic. These U heres are essentially given by the time derivative of psi. And so once we do this, the 0th moment without any of these U's is just a power spectrum, once you Fourier transform at least. The first moment is the mean pairwise velocity that you can. The first one is the mean pairwise velocity VI of k, which you can measure from a simulation just by taking 2 points, measuring the velocity differences, and the density weighting will be automatic given that you're taking halos from simulation. And similarly, the second moment is the pairwise velocity dispersion. And you can measure that again by measuring v squared of the difference between points in simulations and calculating the monopole and the quadrupole. Okay. Finally, a nice feature of LPT is that it predicts these velocity statistics with the IRE summation or at least the resummation of the linear displacement naturally produced. And so finally, what we're left with is a prediction for these kinds of multipoles of velocities as a resummed integral of the bias contributions plus the independent stochastic terms. Okay, so how do we do? Really fast. So how do we do? Here, this first panel here is the power spectrum from 4x4x4 simulations from the NL group, and you can see at redshift 0.55, the power spectrum is really well produced. And now going here, this is the pairwise velocity. And what I've shown here is the contributions from B1 with just linear theory in orange, and then adding the nonlinear biases in green, and finally the counter terms in red, and finally with the stochastic terms also added in blue. And you can see that at intermediate scales here, at k of about 0.15 or 0.2, the stochastic term is doing a lot of work. If you try to fit these in simulations, it is very hard to get the amplitude right. Or, I mean, you cannot get the amplitude right if you do not include the stochastic term. Up here is the monopole of the, so this is the 2-point function of the velocities. And you can see again, it's very important to have this, as one might expect, the sort of variable random velocity term of the stochastic contribution to get from the red curve to the blue curve. And finally, something that's a little bit puzzling is that it seems to be kind of hard to measure, to reproduce, at least in one loop, the quadratic, the quadrupole of the pairwise velocity. So the scale of fit is dramatically reduced compared to the first two things. And it's a bit strange because sigma 2 is actually has a stronger dependence on linear theory than this one. But well. Okay, so, but as I said before, just stopping at n equals 2 is not very sufficient to model RSD. One really needs to go at least to n equals 3. And because n equals 2 is already kind of hard to model, at least in its full angular dependence, we're lucky that there's a small shortcut one can make, which turns out to be true, which is that the third moment is very dominated by random velocity. And so in particular, it is dominated by a term which comes from contracting in a third moment a density with a velocity, which is given by the long modes, roughly the v of k, a vk of r, which is just a pairwise velocity. And then a contracting between the velocities that is given by the short mode sigma squared. So, the pairwise velocity is sigma squared e. And so when you put this together, what you get is a contribution to the power spectrum that looks like k squared mu to the fourth p of k. It turns out that this is a very, very good approximation for modeling register distortion. And in fact, it's the dominant contribution if you look at this compared to data. Okay. So finally, let's put all these things together and see what we can do. So the recipe for producing the redshift space power spectrum is these velocity expansions for these velocity expansions. The ingredients for the velocity expansions are these velocity moments, which we can predict using one loop Lagrange perturbation theory. Specifically, the ingredients are the long modes given by one loop LPT plus counterterms plus the stochastic contributions which characterize the random velocity. An important note is that many of these terms end up looking very, very degenerate when you look at them, when you combine them into the redshift space power spectrum. For example, the counterterms in the first and second moments both give things that look like k squared mu squared p of k. And if you look at all these terms in combination, you end up with a set of terms that is essentially that can be mapped directly to the Eulerian UFT approaches we've heard about. So how do we do? Using the exact same fits as I showed you before, here I've shown going to n equals 3 using the sort of ad hoc using the sort of stochastic prescription for the third moment. You get the solid lines, and so you see with a full model, you can get all these wedges to percent precision out to k of 0.25 without doing any additional adjusting. But if you only track up equals n equals 2, your predictions start to diverge pretty quickly for the higher angles. If we look at the multipoles, which are a common method of data compression, you can see that the effect is even more pronounced. So if I only go to n equals 2 without the stochastic contribution at n equals 3, the quadrupole diverges. The quadrupole deviates from data very, very significantly, even at moderate scales. And a sort of interesting note to make here is that the quadrupole diverges from data even faster than the highest angle wedge, and this is an interesting property of the multipoles in that it picks out the angular dependence of the it picks up the angular dependence of these errors. Right? So when we use perturbation theory, we expand in mu, and the multiples pick out the fact that we're necessarily missing the next highest order in the mu expansion. Okay, so to conclude, the perturbative models of RC are roughly equivalent to different ways of expanding velocities. To model the percent level, what we need is to model the first 3 moments of the velocities. And higher moments are in fact only marginally helpful as the random velocities kick in and become arbitrarily complicated. LPT plus effective corrections and stochastic corrections lets us model these consistently. Let us consistently model both the velocities and the register space power spectrum. And finally, let me close by talking about what we haven't done. One thing we haven't done is to resum all the linear velocities. This is because, well, it's not impossible, but this is because let me not actually. This is because in this approach, at least, the real space velocities that we deal with do not do not require the resummation of velocities, whereas the register space power spectrum does. But I should mention that the Gaussian streaming model does more or less effectively resum the linear velocities and also belongs to the same class of models. Okay, I think I'm about done.
Time for a couple quick questions.
Oh no.
So how many free parameters do you actually have in the PT1.25?
How many free parameters would I have? I think I would have. Let me count. I think I would have 9, maybe 10.
And that's just for mating, right? I mean, you had satellites and all of that, and you go up.
I mean, satellites would be modeled using the same parameters. I don't think they would require more or less parameters.
Why range of cable masses?
I mean, for each population you model, you would need, you need more bias parameters, right? But I don't think this is. I don't think you would need more if you have different. No, I don't think you need to treat satellites particularly differently in this approach, right? I'm not sure satellites have to be treated differently. I mean, they have their own velocities, but they're subsumed into these parameters.
When you combine two populations, then no parameters go up, right?
Okay, yes. If you have 2 distinct populations, you would need.
That's what we have when you have satellites.
No, but I mean, you can't distinguish within your. I mean, within a population that has centrals and satellites, you treat them as the same, right? I mean, you treat them with using the same sort of summary parameters. They're not. Yeah.
More questions? We're feeling a need for coffee. Okay, let's break here, and I guess we come back at 11.
I'm very jet lagged.
Sorry about that. What do I push to stop recordings?
Well, stop sharing. Great. Okay, the menu's not up, so that's great.
If you're ready, you're all set up.
Yeah.
That's good. I'll give you a 5 minutes.
Yes. Thanks.
Okay. Okay, we'll start the second half of the session. To lead us off is Ariel talking about constraining Lambda CDM with Galaxy clustering.
Thanks. First of all, thanks to the organizers for the invitation. It is a pleasure to be here. This is the first time I'm here as an adult, but I used to live here because my father is a mathematician. He did a postdoc here in Berkeley shortly after I was born. So until I was 2.5, I lived here. Of course, this was a really long time ago. Yes, so today I will talk about constraining cosmological parameters with galaxy clustering measurements. In particular, I want to focus on Lambda CDM. And this is work done with a lot of people, and I just want to highlight the my main collaborators on this. So this is an outline of my talk. I will show anisotropic galaxy clustering measurements from BOSS. I will try to highlight what is the information content that they contain. Then I will talk about the modeling of these measurements and how we can use these models to extract cosmological constraints, combining BOSS with Planck and just using BOSS data alone. And then I will finish with some short discussion, if there's time, on the consistency between low redshift measurements and Planck data. So just a summary to say what we were trying to do. So now we live in an era where a variety of cosmological observations have really cemented the Lambda CDM model as our standard model. So what we want to do is to stress test this model. Now, present day CMB measurements are accurate enough to give us good constraints on the basic parameters of the Lambda CDM model. So what we can do is to use those CMB constraints to predict what is the redshift evolution of the expansion history of the universe and the growth rate of cosmic structure. And then we can try to measure these things directly at low redshift and compare our measurements with the predictions as a stress test of the Lambda CDM scenario. And the good thing about galaxy clustering is that it provides us with both of these types of observations. And this is the main driver for the construction of these increasingly larger galaxy redshift surveys. And today, the largest galaxy redshift survey available is BOSS, the Baryon Oscillation Spectroscopic Survey. I don't need to say anything about BOSS. You know everything. I will just say that it contains over 1 million galaxies in a redshift range from 0.1 to 0.7. And yeah, we did already a couple of years ago a lot of analysis of extracting cosmological information of anisotropic galaxy clustering measurements from BOSS, measurements like this one that shows the two-dimensional correlation function as a function of the S perpendicular and S parallel. And it shows, lots of interesting features, and these features contain cosmological information. The main information comes from the BAO peak, this ring-like structure that we see here, and also redshift space distortions that are squashing the contours along the line of sight. So this information essentially gives us distance measurements, so the measurements of the angular diameter distance and the Hubble parameter from the BAO, Yakov-Paczynski distortions of the BAO ring, and the redshift space distortions give us information on the relation between the velocity and the density field, and this can be also expressed as constraints on this quantity F times sigma. And this is why this constraining these quantities has been the main focus of lately of galaxy clustering measurements. So in order to extract this information, we use statistics like multiples or wedges. So just to say what the wedges are, in case you're not familiar with this, this is just an angle average of the two-dimensional correlation functions over wide bins in mu. So this is just like a really low resolution version of this map. So if you just use essentially 2 angular bins in the 2D correlation function, you get 2 correlation functions. This is what they look like. And if you use 3 bins, you get 3 correlation functions, and that we call wedges. And these are then measuring the correlation functions of pairs primarily aligned in the direction parallel, intermediate, and transverse to the line of sight. They all show the BAO feature, and the differences in the amplitude and shape of these wedges are caused by redshift space distortion. And you can do, of course, the same in Fourier space, and these are what the wedges look like on the same data set, and the color coding is the same. And for the final BOSS analysis, we use these measurements to extract cosmological information, and for that you need a model. And the model is shown here by this solid line. This is the best fitting Lambda CDM model to the combination of Planck data with BOSS. So separately for these 2 data sets, we got completely consistent constraints from configuration space and Fourier space. So we'll just say something about the model that we used for this analysis. So this is a one-slide summary. What the recipe that we use for the 2D power spectrum as function of k and mu can be written as a product of two functions. One, this is typical for many other recipes as well. One of these two functions is the non-virial power spectrum, that is the nonlinear power spectrum that describes the effect, the redshift space distortion effect of the coherent flow of matter towards overdensity regions. And this power spectrum is then multiplied by a factor that is usually referred to as the fingers of God factor that describes what is the effect of deviations essentially from the non-virial power spectrum. And then there are layers in the modeling of this that include, first you need a treatment of the nonlinear matter and velocity fields, then a prescription for galaxy bias, and then also to model redshift space distortion. So we'll say a few words about these things. What we use then to describe a nonlinear matter clustering is GRPT. This is a new recipe to describe the nonlinear clustering. There is in RPT and its extensions, you always have this problem that in the RPT describes the nonlinear power spectrum as a sum of two terms. One term is just the linear matter power spectrum times a propagator, and a second term that is a mode coupling power spectrum. And the problem is that as the first term, this propagator is resummed, this breaks Galilean invariance. And GRPT is a prescription to renormalize also the mode coupling power spectrum in a way that is consistent with the propagator. And this is a comparison of the predictions from GRPT shown in orange against the matter power spectrum from the Minerva simulations that we run at MPE. This is a set of 300 dark matter and void simulations. Alex also referred to these simulations in his talk. The resolution of these simulations is modest, maybe, but this is enough to resolve the halos of that host the Bose galaxies, and that was the goal of the project. Okay, so then you see that the predictions from GRPT actually give a very good description of what we find in the simulations up to a case larger than 0.2. This is just the matter clustering. Then you need to add galaxy bias, and this is the same recipe that Alex described in his paper, in his talk. So we have local bias parameters and non-local contributions. We saw that we can just set that gamma 2 has almost no impact on our predictions, so we can just set it using the local Lagrangian relation. But we saw that it was necessary to vary this gamma 3 minus parameter that is related to gamma 2, 1 in the notation in Alex's talk in order to retrieve unbiased cosmological constraints. So our prescription for bias has 3 free parameters. And then we need to add redshift space distortions. The modeling for this is very similar to TNS. So I won't say much about this, but the main difference is that the shape of these fingers of God factor is not just a Gaussian, it includes an additional parameter, a virial, that represents the kurtosis of the velocity distribution, so deviations from Gaussian behavior on small scale. And we then have 4 free nuisance parameters in our model, the 3 bias parameters and a virial. So we tested this recipe using HOD samples on the Minerva simulations for low C and C mass. This is an illustration of that. These measurements here are the mean of these HOD samples from Minerva. The 3 wedges, line of sight, intermediate, and transverse, and the solid line is the best fitting model to these measurements using the recipe that I just described. On top of these tests using Minerva, we also ran other tests using the CAP-SKY mocks from Bose and these challenge boxes that Guido also referred to in his talk. And essentially the conclusion from all of these tests is that we can retrieve the unbiased cosmological constraints or unbiased constraints on the BAO and redshift space parameters. So using this, then we can extract cosmological constraints from the data. And in general, the approach was always to use, we were interested in constraining deviations from the lambda CDM framework. And as we know, the CMB is very good at constraining the CMB parameters, but as long as you deviate from the standard lambda CDM parameters, the constraints from CMB data alone offer really strong degeneracies. And this is one example of that. These are constraints on the dark energy equation state parameter, assuming that it is a constant parameter as a function of omega matter that you obtain. These are constraints, 1 sigma and 2 sigma constraints from Planck, and they show this really strong degeneracy. This is something that is well known. But when you combine CMB data with BOS, then you break this degeneracy, right? And then you get constraints on tight constraints on deviations from the lambda CDM parameter. And this was the game. So you can improve this a bit if you add also supernova data, but this was the game that we were trying to play from this final analysis, trying to constrain deviations from the lambda CDM scenario. Now, since then, the focus of the community has shifted a bit. So now the discussion in the community is not that much about constraining deviations from lambda CDM, but about testing the consistency between different data sets within the lambda CDM framework. Right? So this is a different question. And when people looked at this using different data sets, they found these intriguing tensions. These are differences between the constraints that are obtained with different data sets, which individually maybe don't have enough statistical significance to be relevant or to really signal a problem, but that are intriguing, as I said before, so they deserve further attention. And one of these so-called tensions is the sigma 8 tension, and this is shown illustrated in this plot. These are constraints from different lensing surveys on omega matter and the value of sigma 8, and this sigma 8 tension is the fact that all these data sets in general prefer lower values of sigma 8 than the ones that you would infer from Planck, again within the lambda CDM frame. And these constraints can be expressed as a function of this quantity S8 that is just a parameter that describes this degeneracy. And yeah, so all of these data sets prefer lower values of sigma 8, of S8 than Planck. So what we wanted to do now in this paper with Tillman, Tröster, and others was to try to see if we can say something about this tension using the data from BOS. So the main reason why we always combined clustering data with the CMB is because essentially this is the information that we get from the BAO peak. And in order to obtain absolute distance measurements, you need the size of the BAO ruler. So this is the angular size and the redshift extent of the BAO scale in classic. So if you get this sun horizon scale from the CMB, you really obtain absolute distance measurements, and this is really powerful to constrain cosmological parameters. And this is why this works so well at constraining parameters like W. If you don't have this input from the CMB, then all you can measure is distance ratios, so distances relative to the size of the ruler. But even without this information from the size of the ruler, or this information is given essentially by the prior that you assume on omega variant, you can constrain the parameters of the lambda CDM model using clustering data alone. And this is a test again, so similar to what was shown earlier in Guido's talk. This is a plot showing constraints on lambda CDM parameters using our measurements from the simulation. So these are the Minerva simulations, HOD samples matching the clustering of log C and CMAS, used separately, and then in the joint analysis in blue. And in all cases, we recover the true cosmological parameters of the simulations. Yes? I didn't hear that.
If you tune the clustering to match the observed sample, but there's a systematically observed sample that you did not report,
so these HOD samples don't match exactly the clustering measurements from BOS. These are just based on HOD feeds from BOS data. So in a sense, BOS is consistent. The data from BOS is consistent with being one realization from these data sets. If there are additional systematics, maybe additional systematics that are not taken into account in the analysis of the data, maybe this would affect the HOD feeds parameters. Okay, then, well, but that shouldn't be. So if you want, this is just a test of the model, the ability of the model to recover constraints from the data. And the volume of each one of these Minerva simulations is similar to the volume of BOSS. So this is similar to what you expect using the BOSS, full BOSS array, slightly better.
So this is not the product. This is just one. Yeah. It's not the product of all the.
This is the mean. We're fitting the mean. But the error bar is the error bar of one realization. So the errors are essentially the typical errors that you expect for one realization, but as the mean is the average for this huge volume, you expect to get really the correct cosmological parameter. That's why they're centered on the true values. Yes. Otherwise, one single realization would shift, right? Sure. Okay, so then we did this using the data from BOSS, and this is what we find. The red contours are the results from BOSS. Blue is, again, Planck, assuming lambda CDM. In general, we find very good consistency between these data sets, but it is also interesting that BOSS prefers slightly lower values of sigma 8, as this is seen in this plot. When you marginalize over the other parameters, sigma 8 is a bit lower than the predictions from Planck. So I will try to make something more quantitative on the agreement between these in a minute. So just a slide on the impact of priors. As I said before, this all depends on your prior and omega variant, or your ability to constrain different parameters depends on the priors that you assume. So these are plots showing 3 different priors, what we call uninformative priors, that are anyway priors on omega variant with a width that is 5 times the 68% constraint from Planck. So this is much wider than Planck, but it's still informative in the sense that if you allow omega variant to vary freely over an infinite or a very wide prior, so it's this the blue, so the blue contours are this informative prior. This is a very wide prior on omega variant. You see that it's essentially not well constrained. If you use what we call wide priors, these are 5 times the error on omega variant from Planck. This is essentially you just recover the width of the prior. And if you use a BBN prior, of course, then this is also determined by the prior. The good thing is about that this particular panel, omega matter sigma 8, is really not sensitive to this prior. So we wanted to see what happens if you combine this with other low redshift measurements, and here this is the same plot that I showed before, but I also included here now the constraints from kids data. So these are lensing measurements that also constrain these parameters independently, also assuming lambda CDM. And yeah, separately they're not maybe statistically significant, or they're not really, well, I will say something about that in a minute, but when you combine BOSS and kids, then these constraints improve significantly. This is almost factor 2 improvement in the error. It's 45% reduction. And yes, the predicted value, the preferred value of sigma 8 is lower than this. So this than the Planck value. So this can be written in terms of this S8 parameter. This is a combination of values of S8 in the literature from this paper, compared against Planck, and we can add the values that we get from BOSS only, and when we combine BOSS with kids. So this showed again this tendency to prefer lower values of sigma 8. So, but then what is the statistical significance of these differences? So we'll just go to the last result. So what we use is this suspiciousness statistic. This is a Bayesian quantity that measures the degree of tension between different data sets. This is a bit difficult to interpret, but the results can be casted as in terms of sigmas tension. So if you just look at BOSS and Planck alone, you will say that BOSS and Planck are completely consistent. This tension is only 0.7 sigma, which is perfectly fine. If you look at the combination of BOSS and kids, then the sigma, the degree of tension between this low redshift data and Planck is at the level of 2 sigma. So this is still not huge, but it's interesting, I would say. Okay, so then with respect to this other analysis that we heard before, and we will continue here. So the good thing about this different analysis is that although we use significantly different modeling tools, so we use a different treatment of nonlinearities and Ricci space situations, our constraints are similar. So it means that this is really the constraining power of the data, right? So these results are not sensitive to the particular choice of the model that you use, and this talks about the robustness of these results. Okay, so I'll stop here and yeah, thanks.
Comments or questions?
This is something that I was told when I was doing talk. That if you have 300 simulation, you put the product. And basically, your error bar is 1 over 2 to 300. So you can detect the systematic.
Yep.
You should be within the true value by 1 over 2 to 300 of what you see. So
Yep.
I think that would be interesting to measure the systematic error because it doesn't look like you don't have any.
So what is relevant, of course, is the relation between the systematic error and your statistical error, right? So if you have a systematic error that is less than 5% of your statistical uncertainty, it is irrelevant, right? So what we try to show with these kind of plots is what is the deviation that you would expect on average from the true value in comparison with the statistical uncertainty that you expect for a sample of the size of box. And as the volume of one of we designed these boxes to have roughly the same volume of balls. The idea was that just using the covariance matrix of the different boxes would give you an idea of what is the comparison of the statistical uncertainties versus systematic deviations. But you're right. So you can, yeah. What?
So it should be 170 close.
Half a sigma systematic error, what?
You have 300 times the volume of balls. It's good told me one. So, and now I just have a finally I can do it. So yeah, you have a 1 over 300. It should be the center value by 1 over 300.
Yeah.
It doesn't look like. So
but as I said before, what is relevant is not the absolute size of the systematic error, is the relation between the systematic error and your statistical error.
The difference is half a sigma. So
but the difference here is not half a sigma. So you're talking about this panel? This difference is not half a sigma. This is the low C. If you just look at the low, well, also the result is. I am not sure, but this is probably less than half a sigma.
But what is it in absolute number? Is it 105?
Maybe less than that, but yes, let's say 0.05.
That's not small, right? That's 6% from there. Right there.
For example, that has a larger statistical uncertainty.
No, because if you divide the error by square root of 300, then you have something a significant deviation of the mean from the true value by 6%.
Yes.
Yeah, it's also somewhat misleading to look at marginalized posteriors though, because the maximum likelihood could be significantly closer to the truth than the marginalized means. So that's another thing to potentially look at.
So
the difference between the maximum likelihood of your constraints and the true cosmology in the full parameter space, not the marginalized parameter space. So this could just be a parameter degeneracy that's showing up in the marginalized.
Sure, this is the value that we quote. So we quote the mean. What we quote in the tables is the mean value of sigma from the posterior distribution. Yeah. And the marginalized posterior distribution. Anyway, yeah, I can check this in more detail. But again, what is relevant for an analysis is the relation between the systematic error and the statistical uncertainty. Then you can ask whether if this would be good enough, let's say, to be applied to a sample that would give you statistical errors that are 10 times smaller than this. And then that's a different problem.
Other questions?
Yeah.
So maybe I can, sorry, on the domain, all models give the same result. Again, I think all models are somewhat similar, and I think, maybe you disagree on this, but I think ultimately there's only one model. As for the electric material, there's only one, here mass equation, there's only one. Of course, this G are thinking out, if we are maybe with some critical details, which are not, of course, we're talking about this will matter at this level of the half a sigma systematic error that is there. And at some level, they're all quite similar, and it's in case in the small quantities that matters. Also, if we go to higher loops in the future. So I don't find it so.
I don't understand the point.
Then the fact that the fact that all models give the same answer, I'm not sure when we look at the level of precision. This plot only shows that there is a systematic error of less than 1 sigma of the data. Okay, but that's not enough.
No, from the joint analysis, the systematic error is much smaller than sigma, right? So it's not just less than 1 sigma, it's much smaller. But it's much less than half sigma in this plot. Okay. But anyway, yeah, so then the statement is that you, from both data, you can use different modeling tools and you will get constraints that are similar with similar statistical uncertainty, because the statistical uncertainty is given by the data. And that these results are robust with respect to the particular model that you use. This is my statement. And I think that
the model is very robust. We don't need to argue about the model. We have a model which is super robust.
So I'm not.
Right.
I'm just saying also that it is very good that we can use different modeling tools, apply different modeling tools to the data and extract a similar, robust, consistent cosmological constraints, because it speaks about the robustness of the results. Right?
Would you say in the electromagnetism class, I'm using two electromagnetic maximum equation for electromaterial? We use one. I mean, one is right, the other is almost right, maybe not so right. I just try to test.
Okay. Okay. All right. Okay, let's thank our speaker again.
So what do I do here, Chan?
Okay, next up, Misha will tell us about cosmological parameters from LSS data.
Hi, everyone. Thanks for having me here. This is really very nice opportunity to meet all the people working in large-scale structure, and I'm looking forward to fruitful discussions altogether. So I'm going to talk about the measurements of cosmological parameters from current and future large-scale structure data, keeping in mind the spectroscopic galaxy clustering data. So my work is based, my talk is going to be based on work in collaboration with Marko Simonovic, Matias Zadaryaga, and Anton Chudaikin, who is now moving for his first postdoc at Perimeter, Toronto. So I'm going to present the results obtained with a new pipeline, which is designed to analyze data from spectroscopic galaxy clustering surveys. So the zeroth order idea behind this pipeline was to be able to consistently recompute the matter power spectrum and other statistics as we scan over different cosmologies. And the main feature of this pipeline, the core idea, is to use the most advanced nonlinear model for the theoretical power spectrum and other statistics, which is based on one loop perturbation theory. It includes all the developments in the field, in large-scale structure theory, all the developments which have been made in the last decade, which crucially includes the counter terms and infrared resumation. And here maybe I should pause for a moment and say that since Lifshitz discovered linear cosmological fluctuations in 1946, there were numerous attempts to build a consistent nonlinear perturbation theory, and essentially these attempts, they led to the development of the effective field theory of large-scale structure, which finally gives you the only one fully consistent Taylor expansion, which relates the nonlinear density field and the powers of the linear one. And compared to previous works, I think crucially that this Taylor expansion has some higher derivative terms, which are called the counter terms, that are also characterized by some unknown coefficients, some unknown parameters, which have to be fitted. Those have to be treated as nuisance parameters in data analysis. So, and these three coefficients, they parameterize our ignorance about short-scale processes, which we will never be able to model using perturbation theory, okay? And here, as Martin is leading the session, I should say that 5 years ago, he had a beautiful paper with Matt McQueen about one-loop cosmological, well, about just cosmological perturbation theory in 1+1 dimensions, where in fact, like leaving aside these terms, you can actually resum all these deterministic terms. And then, even if you do so, you never improve upon linear theory. So you must absolutely include these corrections. And okay, 5 years ago, I just started doing my PhD, and for me, this was a clear case example showing that this is indeed the correct theory to study. Okay, then we have implemented this essential Taylor expansion with everything in the first estimation counterterm, implemented this as a module to the class code, and we use the FFT-log method, which really allows us to compute the power spectrum super quickly. And as it is implemented in class, now you can take advantage of all the benefits of class, all the virtues. So it's very user-friendly. If you know how to run class, for you just pressing a button and you get all the nonlinear spectra. Then it easily scales with a number of parameters. It incorporates all possible physics and effective extensions of dark matter, dark energy, everything's already included. No hard coding, you can easily interface it with Monty Python, okay? And we're going to release the code soon, hopefully next month. So in my talk, I'm going to present 3 different applications of this pipeline. First of all, I will show some results of the analysis of high resolution body simulations. Then I will apply this to analyze the Bose data, and then I'll present a forecast for future surveys like DESI and Euclid. So once we had the pipeline, we decided to test it by participating in the blind perturbation theory challenge organized by Masahiro Takada and Takahiro Nishimichi. So all the data is available online, and if you feel good about this model, please, I encourage you to go and participate in the challenge, because this is the idea to finally pin down, to understand what is the good theory for future service, okay? So the task was the following. So if you go to this link, you will find the high resolution and body simulations. So you find the power spectrum of Bose-like MOCs with a total volume of almost 600 cubic gigaparsecs, which is 10 times bigger than Euclid or DESI will have. And the task is to measure the input cosmological parameters, which are unknown, okay? And here on the left, you see the challenge power spectra, the monopole and the quadrupole. So you see the best fit curve and you see the data points. You don't see the error bars because they are super tiny. Here you can see them in the residual plot. And you see that on the monopole, the error bars are 0.1%, and 1% is that huge. So we're able to, well, fit the spectra and recover true cosmology with 0.1% accuracy. Okay, and here I should maybe emphasize again that this accuracy is much better than the accuracy of most of the n-body simulations. With n-body simulations, it's very painful to get to 1% precision. There are very few high resolution body simulations, and with perturbation theory, we can easily get to 0.1% and even better. Like for us, it's not a limit. So then we applied this pipeline for the real Bose data. Here you see the results for our baseline analysis. So in the baseline analysis, essentially we fixed all the parameters to some priors. So all the parameters but H0, omega matter, and sigma 8. And we're able to measure, well, essentially these 3 parameters. And for H0 and omega matter, the precision is comparable or even better than Planck. And so the final Bose data is divided into 4 data chunks that represent different galaxy populations. For each data chunk, we used 7 nuisance parameters, so 4 parameters describing nonlinear bias and 3 parameters describing nonlinear edge space distortions. And of course, the natural question that arises, okay, how would these constraints change if you include some more parameters in the fit? And this we also did. So we included NS, you can measure NS with some 5% precision. Then you can also measure omega baryons, but I think that both, like we can actually trust the measurement of omega baryons from Planck, because this measurement is model independent, because you cannot, with any new physics, no new physics can produce the same pattern of the bio-wiggles in the Planck data, okay? So we can take it from Planck, or if you don't like Planck, we can take it from BBN, but I think omega baryons, we can trust. It's not vital. We can also fit omega baryon. We'll measure it with some precision. The constraint on H0 will not degrade much, okay? But in principle, you can explore the full likelihood. You can set some bounds on neutrino mass. These bounds are not very competitive with CMB, but still. So I have some backup slides about this prior. So if you want to learn more, ask me later. Here I should maybe say that the main conceptual difference with respect to previous Bose analysis, as Ariel was telling us, is that somehow previously the main idea behind Bose was to constrain dark energy and in combination with Planck. And for this goal, having this goal, it's okay to have Planck price, to put Planck price on omega baryons, omega CDM, because we know from Planck these parameters much better from Bose, okay? So in our work, essentially, the only twist is that you don't need this price, you don't need the prior on RD, you can measure RD from the power spectrum itself, okay? And the shape information, in principle, is able to constrain everything. In other words, somehow, if Planck exploded, still would have very precise H0 and omega matter measurements, even without Planck. But okay, hopefully, luckily it didn't explode, and everything's good. But in principle, okay, we had some backup plan. There was a backup plan. All right, so where this information comes from? Let's take a look at the dark matter power spectrum at redshift 1000, right after recombination. So this is the seed for structure formation. So this power spectrum has many features, in fact. Of course, it has the BO wiggles, well know. Then it has some peak, it has a peak, it has some slope, which is controlled by the same parameter that also sets the position of the peak, which is K quality. Then it has a tilt, and tilt is not degenerate with the slope. Then it has a baryonic step. Somehow it's not a very famous feature, but even though it's very significant, that's why I produced this plot to show that there is a Jeans-like suppression due to omega baryons, which is 50%. And that's why you can measure omega baryons thanks to this feature. And you can measure by the RD, even in the absence of the BO wiggles, because this scale is set by RD. You can measure RD even if there were no BO wiggles. So now, what happens after redshift 1000? Very boring. The power spectrum just in lambda CDM just grows. Okay, so you rescale it vertically. If you do now parameter constraints, first of all, you use these features to constrain the shape parameters, omega baryons, omega CDM, and NS. So this you constrain in the first place and totally regardless of any late time evolution. So these constraints, in other words, those are principal components of the shape. Okay, you measure those. Then second, you constrain the freedom of essentially rescaling your power spectrum in the horizontal direction, okay? Because you have some features, in order to put them on the sky, you have to multiply by some distance. In lambda CDM, it's only H0. This is the only parameter that controls the distance. In some general setups, it is the volume average distance dV, okay? So you constrain the horizontal scalings, it gives you H0. Then you constrain the vertical scalings, in general gives you F sigma 8, because you only get to measure the velocity power spectrum, not the actual density power spectrum. But in lambda CDM, it's only sigma 8 because F has been already fixed in terms of omegas. Yeah, little omega is the physical density is rho, really, okay? So little omega CDM, little omega B, H0 already constrains F, okay? And then there is another additional effect, which is a beautiful effect for studying dark energy, but in lambda CDM it's absolutely redundant. It's the Alka-Paczynski effect, which allows you to measure in a model-independent way the radial and the angular distances. Okay, in lambda CDM, so you have already measured all the parameters from these effects, so you get nothing from Alka-Paczynski, and this, by the way, was already emphasized in the original paper. But for dark energy, this very strong effect, this very good thing. Okay, so we have done this for Bose. What is going to happen in the future? This we already know because we did a forecast for a Euclid or Daisy-like survey, and the main idea behind this forecast was to be as realistic as possible. What if you give me the data right now? What if Euclid already measured everything, you gave me the data? So we use the same pipeline, we use the same full nonlinear model, we run the whole MCMC with a bunch of nuisance parameters. I think that in total we had 50 nuisance parameters and all cosmological parameters without any priors, also without the prior on omega baryons. Then the idea was to keep totally agnostic about bias, about these biases and nuisance parameters. So we put no priors on them and marginalize over those. And by doing this, we also marginalize by other systematic effects like fiber collisions or redshift errors, because these systematic effects, they have the same K dependence as the counter terms. It's K squared or short noise. That's why when we marginalize our new parameters, we also marginalize our possible systematics. And we use the same data class as we have now. So we have done all this, and we have found, okay, first of all, we have found that you will be able to measure the cosmological parameters of lambda CDM with the same precision as we have from Planck. So here, for example, in this plot, you see the posterior for little omega CDM and Hubble. Okay, this is the dashed line is the current, the actual Planck contour. The red line is the power spectrum constraints from a Euclid-like survey. Then if you add the bispectrum, then this curve narrows down. If you combine it with Planck, the most important thing is that these two contours are orthogonal to each other. When you combine, you gain by a factor of u, okay? And in this analysis, we didn't use any priors, even like on omega values, we didn't use a prior. Crucially, using this information, you will be able to constrain the neutrino masses, and you will be able to get constraints much better than we have now. Already with the power spectrum of Euclid, you will get one sigma error bar essentially of 30 milli-electron volts. If you add the bispectrum information, you will improve it by a factor of like by 30% or so. So now it goes to maybe 15 milli-electron volts. If you combine with Planck, it goes all the way to 13 milli-electron volts. In other words, you will be able to measure the sum of the neutrino masses, even the minimum one at 5 sigma, using the pipeline which is already built, which is already there. And I guess that it answers the main question of this workshop. Are we ready for the future? I guess the answer is yes, at least from the perturbation theory side. All right, still there are some improvements that can be done. So let me discuss these improvements. One very important improvement is the use of the theoretical error. In perturbation theory, we always compute things at up to a certain order, and we neglect higher orders. Here in this analysis, we did one loop perturbation theory, we neglect two loops. But still we know that the two-loop contribution is not some wild function. We have some estimate for it. We know it with some 10% precision. We cannot add this to our theoretical model. Then we can add this to the covariance, because in the covariance, it's okay to be 10% imprecise. So the idea is really, okay, this is my likelihood, this is my data vector, this is my theory vector computed at one loop. This is my two-loop contribution, which I add here, and then I marginalize over this two-loop contribution. And if I do this, I will find a new covariance, a new contribution to the covariance, this theoretical covariance, which has the following form. So its amplitude is set by your estimate for the two-loop matter power spectrum times some exponent of the difference between k-bins. Essentially, this is the off-diagonal part. So the most crucial thing about the theoretical error covariance is that it's off-diagonal. Okay, by the way, this is very simple way to estimate off-diagonal covariance for any analysis without having to run thousands of mock simulations. Well, anyway, this off-diagonal element essentially reflects the following fact that the two-loop contribution is not some wild function. If it moves one point here, it will also move the other points. So it moves the data points coherently if you add it or remove it. And this is reflected in here. And from this, for instance, it's clear that even if you blow up the error bars and go to higher k-maxes, still you'll be able to get some new information, because there are features like the BO feature, which cannot be modified by the two-loop contribution, okay? And also the equality. K-equality is very infrared scale with respect to k-nonlinear. That's why you still will be able to constrain this. So here on the right, I'm showing you the result of fitting some high resolution and body simulations. So cosmological parameters with and without the theoretical error. So let me do first the standard analysis, just increase the k-maxes. So I started some low k-max. Okay, I fit more or less everything. I'm unbiased. I keep increasing my k-max. I quickly get biased. Like my sigma 8, my amplitude gets biased. If I were to do k-max, I would say, okay, I have to stop here. I would just see, okay, these things, they fall apart. I shouldn't take this. But if I take into account the theoretical error, then I'm able essentially to go to arbitrary large k-max, and then I will take advantage of these BO wiggles of some shape information, which is still already there, which cannot be modified by the two loops. Okay, so I got, those are the results obtained with the theoretical covariance, and crucially for things like H0 or little omega CDM, the improvement is factor of u. so this is one improvement which I'd like to implement in data analysis. The second one is the treatment of fingers of God. Okay, I'll be really quick. So there was a beautiful paper by Urish and collaborators, just devoted to the theoretical modeling of ratio space power spectra. And one of the main points of this paper is that there is a way to remove or sufficiently suppress fingers of God. Okay, fingers of God are some noise produced by virialized motions of galaxies in halos. Okay, and fingers of God really, they just remove information. So here in this plot, okay, those are the monopole power spectra for different galaxy samples. And this is the quadrupole. And you see that essentially this blue curve is the quadrupole as we get it from both, okay? And the orange one is the quadrupole, say, without fingers of God, which you can do if you remove the satellites, because the fingers of God are mostly produced by satellites, okay? The centrals do not move that much with respect to dark matter halos. And you see that this fingers of God suppression is a very strong effect at K 0.25 inverse megaparsecs is an order 1 contribution. So clearly perturbativity is jeopardized, okay? But if you remove the satellites, you suppress fingers of God, you go to higher K nonlinear, then you extract more information. So I guess that one very important thing to be understood in the future is how to isolate fingers of God or remove them. Maybe one way to go is to use ratio space wedges, because then you can just throw away the mu equals 1 bin, and then you live without fingers of God. Maybe it's a better idea to do multiples. All right, so I'm done. So let me summarize my talk. So perturbation theory is very precise. It's 0.1, already now we have 0.1% precision, and it can be made even more precise. Then it's very robust. We tried many different, we ran many different tests, and we were always able to recover unbiased cosmology within the expected statistical error bars. Right now, if I apply perturbation theory to the Bose data, we can find that Bose rivals Planck in terms of precision for H0 and omega matter. And in the future, we'll be able to constrain all the cosmological parameters better, well, similar or better than Planck, and crucially to detect the neutrino mass at 5 sigma. Thank you.
Question? As a three-point guy myself, I'm very excited that my spectrum seems to add to the neutrino mass, but I did wonder, first of all, what different bias parameters and other things would be marginalized over in that forecast?
Okay.
Do you think that matters a lot?
Oh yeah, it matters a lot. Yeah. So in this forecast, to get this contours, essentially we used only the 3-level bispectrum. And so essentially we had only two bias parameters, but these parameters you also have in the power spectrum. That's why you gain when you add this. Of course, if we add one loop, you have more freedom. You have 11 nuisance parameters now. In this forecast paper, we did an ersatz analysis where we use the K max as if we included one loop contribution without introducing new nuisance parameters. And the upshot was the following, that without the Planck data, the improvement was very big, like factor 5 or 3 or something. But with the Planck data, the improvement was more modest, maybe some 20%. So from this forecast, I got an impression that the bispectrum is also, I mean, it helps, but its help is limited. I think so, yeah, because, okay, the bispectrum is important because it allows you to break degeneracies, but also you can break degeneracies with Planck. So at this point, the bispectrum doesn't add much. Crucially, the bispectrum doesn't change the orientation of this contour, say. You see it only like it narrows this line, but it doesn't actually shrink it. Yes? Because we had an agreement to present result at some K-max, in fact. So at point 2, we submit the results at point 2 because we decided to be a little bit conservative. But in fact, we find out that we can feed things even at higher K-maxes. But also you should understand that this volume is much bigger than Bose. If I rescale the covariance to Bose, then we're able to go to much higher K-max.
Why is showing this 0.1%? What happens above that?
Well, above that, okay, until 0.2, essentially, you're able to fit everything. So I could have shown the plot up to 0.2. I'm showing you 0.12 just because we agreed this is consensus result that was submitted to Masahira. Fine. For the challenge, the covariance matrix was diagonal.
Or even for this estimate, it was diagonal.
For which estimate?
The one you were showing right
now? Yeah, for the PT challenge, the covariance was given to us. It was given diagonal, but I think it doesn't on these large scales. It doesn't actually matter. I also did an analysis with the off-diagonal covariance, and then the constraints didn't change much. Yeah, this is essentially. Yeah, you mean in this or in the challenge? So in the challenge, the covariance was based. They had 10 different realizations. It was like diagonal extract from these 10 realizations. Yes. So we fitted the mean of essentially 10 realizations, and then we scaled the covariance by square root of 10.
What does it mean no need for omega b?
Oh, in this analysis, you can actually measure omega b. With Euclid, you'll be able to measure omega b with precision better. Right now, you can measure omega baryons from both data with precision 20 times worse than BBN, okay?
Yes, but then it will also give you a huge error on H. If you
no, here, no prior, and still you're able to measure H. No prior, you're able, if I put this prior, then my H will be twice smaller, my H posterior.
It seems to me that if comment about B1 loop, it seems to me that would be interesting. If comment one goes higher order, to give an order in an endpoint fashion, should go to one less order in an endless plus one fashion. There is if one does the one loop by spectrum, can do the three-level
trust spectrum, right?
And so on and so forth, because it's the same kind of amplitude.
Exactly. Yeah.
So I think this would be nice to see also.
Yeah, to add it, yeah, sure, yeah, I agree.
Yeah, just a comment. I think we should be cautious about these expectations for high precision of measuring neutrino mass in terms of real galaxies, because if you take about simulations including massive neutrinos and build galaxies in a simplistic way as you want in the simulation, you see that these constraints become much looser. And so I think, although of course we are all going after also this, there is a lot of work to do on actually modeling the galaxy distribution on top of the theory. It's not only a matter of bias parameters, but really understanding how the galaxies that we will use will trace matter. I wish we could have that precision, but at the moment, you just compare what you expect from expecting to measure the matter power spectrum or measuring the galaxy power spectrum. And you try to constrain the figures, there's a difference of the model magnitude in general. So there's a lot to learn there.
But do you mean if you try to analyze this data using some emulator or something?
Well, I think this is essentially what you see at the moment if you take numerical simulations, including the neutrinos, and you say, well, what do I get if I just use the theoretical power spectrum with the bias description, etc., you get what you get. Or if I measure the power spectrum of the galaxies I created in my simulation as they have data, and I try to constrain my neutrino mass with that, and you get significantly different results. You know, the yellow bars are much larger.
I see, but I think that yeah, I think that okay. In theory, we know how to describe it. Okay, in theory, there are no this. I mean, if you do simulations, yeah, I think it's a big problem how to properly include neutrinos, for instance, in the body. There are many groups working on this, so I understand that this is a big problem.
The problem is not how. Okay, there are problems with how to put neutrinos, but the problem I think is that you are going to use galaxies. So
right.
Galaxies trace the matter power spectrum in their own way. It's not a matter of the bias function is very complicated. That's what I'm saying. And This is what you see in practice.
Are you referring like to the fact that this bias expansion at some point, like the vanilla bias expansion is not sufficient? Yeah, the work claims like this. Yeah, I'm actually right now looking into this. Yeah, this is a legit point. Yeah, I'll be happy to discuss this. Yeah, I agree.
Sure. Yeah, what's your K-max on the BOSS analysis?
0.25.
So, and are you using the standard nearest neighbor correction for the fiber collections?
In fact, we're using the full window, also the effective window function. We have done both the effective window function, but now there is absolutely zero difference. The difference is smaller than 5% on the posterior. Everything is absorbed into the counter terms.
Okay, I'm surprised that there's this little difference between using F1 analysis and using standard nearest neighbor. Because the power to measurement should be, it scales larger than, I mean, Chang would know this much, I'm just looking at his paper right here. It scales larger than K of 0.1, you get bias measurements to the power spectrum of the nearest neighbor correction. But I mean,
but if you don't include, okay, for the monopole, if you just vary the shot noise absorbs everything, right? Then for the quadrupole, the baseline analysis of both didn't have any nuisance parameters. With the EFT, we have nuisance parameter for this. We marginalize, it's totally absorbed into these parameters.
Okay, let's thank the speaker again.
Can we do it on here? Let's do it on here. Yeah, we're using one.
And the last couple for lunch, telling us about logical analysis of LSS.
Okay. Hello, my name is Byung-hee, and I'm graduate student at UC Berkeley. And today I'll talk about the LSS analysis of the BOSS data. And I'll both talk about the perturbation theory model and also the emulation, the base modeling to constrain F sigma 8 parameters. So first, the overview. So I take the perturbation theory model developed in Roche's group and apply it to the BOSS data, showing that our model provides a competitive constraint on the growth of structure. And when we analyze the posterior of the cosmological parameters of our interest, we use a new optimization-based method called LO, which is sacred as MCMC, but its computational cost is only a fraction of MCMC. But there are limitations of this perturbation theory approach, because it cannot accurately capture the effect of nonlinearities especially on small scales. And it's kind of unclear how sensitive the cosmological growth of structure measurements are to the small scale, the physics. So one of the most promising methods is to include this small scale information, and it's the simulation-based modeling. So the perturbation theory model I discussed in this talk also includes a calibration from simulation for key terms. And in the second part of the talk, I'll present the galaxy power spectrum emulator developed by Elena Massara, and how I use this to constrain F sigma 8 on the simulation data. And lastly, I'll briefly discuss what I plan to do with the data from the upcoming, the future, the spectroscopic survey like DESI. Okay, in the first part, I'll describe this perturbation theory model developed by Nick Hand, and how it's different from others, and what pipeline I did develop for the analysis, and lastly, the RSD measurements of the BOSS data. So in the redshift space, we can decompose the contribution to the galaxy, the overdensity field, into the contributions from the C, which is the central, and S, the satellite galaxies, as shown in the first equation. So then the power spectrum of the galaxy power, this galaxy density field, can be written as the second equation. So we see the combination of the auto and the cross power spectrum. Here we wish to separate the one halo and the two halo, the terms. So the one halo means the contributions, the correlations of the galaxies in the same halo. And the two hello is is coming from the galaxies in different hellos. So to do this, we further decompose the central and satellites into subsamples. Here we call it type A and type B. Here the blue dotted circle indicates the hello. So for the central, type A means the central without any satellites, and for type B, it's the central with the satellites. Similarly for satellites, like type A means the satellite with no neighboring satellite, and type B is the one with the neighboring satellites. So the advantage of this is like we can easily model the one hello, the contribution. Like, so here we can see the one hello term is coming from type B central and satellites and between type B satellites. So we can write down the equation for the two hello terms and also one hello terms, and we see where the contribution is coming from. And we write down this term as a white noise. And the finger God effect is a full like nonlinear process, so we cannot like accurately model it using the perturbation theory. So we use some damping the function. So here we use a modified Lorentzian of this form, and here the sigma v denotes the velocity dispersion. And we see, as shown in the figure, we see that we can accurately model the finger God effect over a wide scale of the wide range of scales, extending to k of 0.4. And one great thing about this model is in most other models, they assume a single velocity dispersion term for the whole sample. But here, we better account for this effect by having a separate velocity dispersion terms for our subsamples. So here's our full parameters of this perturbation theory models. And I'll briefly talk about the likelihood pipeline. And to measure the Pop spectrum, I used a Python package. It's called Embodykit. And here we use the Yamamoto estimator. And using this, we write down the multiple estimator right here. And second, we need to account for the effect from the survey geometry when we compare our theory model to the measured Pop spectrum. So to do this, we compute the window function multiples in configuration space using a pair counting algorithm implemented in Embodykit. And as you see, it's here the resulting the multiple of the Boss CMS NGC samples. And on the right, the effect of the convolution is shown here. And the last piece we need is a covariance. Here, the simple one we can use is the Gaussian covariance from Grip et al. Here. And when the mean number density n bar is varying in redshifts, we can write down the per mode variance as the second equation here. And alternatively, we can also use analytical model to get the nearly diagonal and full length covariance, which is called the disconnected covariance. Here we use the model from In's paper. And compared to previous works, which only captures the size of the geometry, but ignores its shape, this has a proper treatment of the window function effect on the covariance. And I would not go into the details, but yes, you can see we compare the diagonal, the one from the Grip et al. Versus disconnected, which are from In's paper, the blue versus green, and they are about the same. So these are the constraints on F sigma A on the CMS NGC samples. And also I am also doing the more complete analysis using the full covariance, which includes off-diagonal and connected pieces, which are important on small scales. So for now, as a preliminary analysis, we get the connected pieces by running PCA on like 3x3, the blocks of the multiples. And we found like good agreement between the analytic covariance and the covariance from like 1,000 patchy mock simulations. And adding these connected pieces increases error by like 30%, but this is like quite preliminary. And so we have all the ingredients now. So we have the measurements, and we have the convolved theory Pop spectrum, the window function effect taken care of, and also the covariance. So we can write down our objective function and estimate the best fitting the model parameters using the map optimizations and using the BFGS algorithm here. And finally, can use the MCMC to derive the likelihood distributions of the model parameters and the constraint F sigma 8 as shown in the figure here. But here in this work, instead of MCMC, we use the new posterior inference method called LO, which gets the MCMC posterior quite accurately, but at a much slower level of computational cost. So in MCMC, we draw samples from probability distribution, but then instead of trying to deal with the intractable computation involving the posterior, we just get the samples from distribution. However, on the other hand, the VI, the variational inference, try to find the best approximations of the distribution among parameterized family. So in order to find this best approximation, we follow some optimization process over the family parameters. So the first thing we need to do is set up the family of the distribution. And for example, say if our target distribution is multimodal, then we can think that if you use a family of the mixture of two Gaussians instead of the family of a single Gaussian, then we can better approximate we can get the better approximation using VI. So how to get the best approximations? So we minimize the scale divergence, which is basically measuring how the one distribution is different from the others. So here's the setup, and say here the X is our data and Z is some parameters which the data depend on, and we want to get the posterior of Z given X, and we write the log posterior LP, and we come up with some model Q. So we try to fit the posterior of the Z to the model Q of Z. So as a first step, we can assume that the Gaussian ansatz of Q, and later on we can make the Q more expressive. And so we can minimize this scale divergence. And however, the minimizing this with sampling is a noisy process, but I will not go into detailed derivation of why it is. So here we take we instead propose a simpler and the less noisy optimization process called LO. So we want to replace this noisy scale divergence minimization with a simpler and less noisy one. So we minimize the L2 norm distance between Q and P, and we call it the LO here. So here we take the gradient expansion of the LP around the sample CK and generalize the LO to the equation below, and we stop at the two expansion term. So we use the gradient here and the Hessian term here. So to briefly explain the advantage, so here we say we take we say our posterior is 1D Gaussian, and then we can write LO as a quadratic equation in the Z, the sample Z. So 3 samples should be sufficient to get the complete solution. And however, the VI is very noisy and it takes many iterations to get the true solutions. And here's the algorithm for the full-length Gaussian cases, but I'll skip it later. And also here, we can certainly go beyond the family of the full-length Gaussian. So here we enhance our model using 1D bijective transform, and we use a family of models that gives skewness and the kurtosis. And we can also use the Gaussian mixture model. So back to the RST example. So if we use MC, then it takes about 10 to the 5 calls to converge. And we have to start from the place where the map converges, and otherwise it never converges. So now instead of we use LO, so we start with map, and then we switch to sampling from the QR model, and then gradually increase the number of the samples. And overall, we need only a total of 125 likelihood the evaluations. And we find that LO gets the MCMC posterior quite accurately. And as I mentioned previously, the greatest advantage of LO is computational efficiency. So LO is about 1,000 times faster than MCMC and about 200 times faster than the VI using the same parameterizations. And now we use this posterior inference method to obtain the F sigma 8 constraint on the boss data. So first, we applying the model to the boss data, like low C and CMS separately. We can see that the monopole, quadrupole, and hexadecapoles are the model quite accurately up to K of 0.4. And here is our F sigma 8 posterior. And you can see that we tightly constrain F sigma 8. And with AP parameter fixed, we get 3% constraint on CMS and 4% on low Z. And this corresponds to a total of 2.8 combined. So a few things I should mention is like the small scale information helps. So compared to the K of 0.2, like we get like about roughly 30% improvement by extending to K of 0.4. And also including hexadecapole, F sigma 8 constraints improved by roughly 35%. So here's a quick summary, and I'll come back later. And in the beginning, like I already mentioned some of the limitations of our perturbation theory model and why the emulation-based model can be useful for future survey analysis. So here in the second part, I'll first go over the emulation algorithm developed by Elena Massara and how I'm using this to constrain the growth substructure. So the structure of this algorithm is shown like here. So with a given cosmology, we generate the nonlinear density field using FastPM. And then like we identify halo using friends of friends algorithm, and we populate the halo using MBodyKit and get the galaxy power spectrum. And in the following slide, I briefly show like how the sampling variance and the residual noise can be corrected and how the BAO wiggles are analytically modeled. So like there are many ways to remove the sampling variance, like without using like many like large number of realizations. But since we are out of time, I'll briefly like I'll skip the sampling variance cancellation part and then go right to the how I use a pair simulation. So basically what I'm doing is first I add the linear power correction term, and then we can use like more comprehensive the sampling variance correction method using the pair simulation, which is basically we assume like the density field is which is a Gaussian, we write it as a complex number, and we generate like two different simulations with the same amplitude and with the phases differing by pi. So we see that the better density field they have like these two better density field have the opposite signs. So using this, we can estimate the power spectrum B1 and B2, which are the power spectrum in the evolved field of the two pair simulations. So and also we also fix the amplitude of the density to 1. Then the initial power spectrum of a single realizations that reproduces the sample average linear power spectrum. So we combine these two methods and they create a paired and fixed amplitude the simulations. So in this plot, we show the performance of different sampling variance like removal method. We take the monopole, quadrupole, and hexadecapole of the redshift space galaxy power spectrum and compare the predictions from this emulator to the ground truth. The ground truth here is the ensemble average from 70 different independent simulations. And we see that the best method is the fixed plus paired simulations, whose RMS error is about like roughly 3 times lower than that of the simulation with no sampling variance correction. And similarly for quadrupole and the hexadecapole. And you see the hexadecapole is quite noisy and difficult to model. And we also do the splining. So we create, but for the time being, I'll skip the spline part and the BAO wiggle part and show how I use this emulator to get the optimizer. So basically the idea was we are using spline function to remove the residual noise. And because spline, like smooth is a function, is not suitable for the BAO wiggles. So what we do, we take out the BAO wiggle from the power spectrum and find the ratio between the linear and the nonlinear, the multiples, monopole, quadrupole, and hexadecapole, and just find the results. And later add back the BAO wiggles with the nonlinear damping term here. And as a result, we see that the monopoles can be predicted within like 1%. So we get sub% accuracy, and quadrupole is also pretty accurate when we also get only a few % error. And hexadecapole is pretty noisy, and we have like about 20% error between this scale 0.1 and 1. And now I'm using this emulator to get the Gaussian power spectrum multiple and use like different optimization algorithms to constrain cosmological parameters. So here, the objective function is data minus model, where the data is the ground truth, the ensemble average of 70 different simulations. And the model is the predictions from the emulator. And we have 7 different parameters, 5 from HOD and 2 from cosmology. And we have F sigma 8 as one of our parameters. And for the algorithm, we use the BFGS and Gaussian-Newton to minimize our optimization, the objective function, which are the data minus model. So we start the optimizer at some initial cosmology and some HOD parameters, which are the red dot in the figure here. And we first need to evaluate find the different gradients. So since we do not have analytic ones, so we run 2 additional simulations, which are the orange dot in the figures. So we have to run like 3 simulations at each step. The reason why we run this 2 additional simulation is to get the numerical derivative with respect to the cosmological parameters. Here we have 2. And also we have to get the gradients of the 5 HOD parameters by running emulator at this red dot, but these are pretty fast compared to running the full simulation. So after we get the gradient for all 7 parameters, we can move on to the next point. And after 2 to 4 steps, we say we are closer to the ground truth, and we say that doing the linear Taylor expansion is good enough. So we write down the quadratic expansion of our objective function and fit for the coefficients of this objective function. And we get the better approximation of the numerical gradients. So here's the results. Here's the method I use to do the optimization. So I'll skip it to the actual results. So when we get the numerical gradients, this is for the cosmological parameters. We also use a spline to remove the residual noise on small scales. And we can see that we only need like few simulations to reach the convergence. So here's the results. So in blue, in red, we get the constraint from monopole and quadrupole. And in blue, we add hexadecapole. And we obtain about like roughly 8% constraint on F sigma 8 on the simulation data we have assumed. And only few simulations are needed to reach convergence in this case. So this is basically preliminary the contour plot of like 7 parameter, 5 HOD here and 2 cosmology. So in summary, so in the simulator, we can reduce the sampling variance with only 1 or 2 derivative realizations. And modeling the Gaussian power spectrum as a spline function and the BAO wiggles, we can have high accuracy, the predictions on monopole and quadrupole. And we only need like few simulations to get the constraint on F sigma 8. So this emulator can be pretty useful for large survey like DESI. So the last question is what can be done with the future survey like DESI. So I can measure the power spectrum multiples from DESI and apply this perturbation theory model or emulator to DESI and doing some cosmological analysis. And we can also get the better, like the hybrid covariance from the disconnected and the connected pieces. Thanks.
How do you model BAO window? Is there a prediction?
Yeah, after we find the ratio of the nonlinear and the linear, the plot spectrum, we just add back the BA wiggles with this damping term here. So we basically get the ratio between the wiggle and no wiggles, and approximate the nonlinear damping term as here, and we get the theoretical prediction for this the ratio.
So it's a full path simulation with wiggle, non-wiggle.
Yeah.
For the covariance, like why did you use the PCA plus the Gaussian covariance for the patching mode? Like instead of the patching mode, you use the Gaussian covariance plus the PCA.
Yes.
Do you change cosmological parameters in your covariance?
Pardon?
Do you change cosmological parameters in your covariance?
What do you mean?
Why do you use analytic this covariance plus PCA? Why not just use patching modes?
Ah, I see. So like for the future purposes, yeah.
Or maybe it would reduce noise in the off diagonal.
And as you can see in the plot here. So the Mach 1, I haven't plotted the Mach 1 here because of the noise in the Mach. Like they do not like mesh exactly to the disconnected plus connected ones. So we.
So you
Yeah.
fix the cosmology.
Yep.
Question.
When you say you had a fixed less paired simulation, so first, what does it mean? And also, why is that one better than
Sorry. So what I mean by the fixed simulation is setting the amplitude of the density field to 1, and why it is better than doing the simple the pair simulation is we can assume that the initial path spectrum of like one realization is like pretty much the average of the linear path spectrum, and so that we don't have to do any like further like the correction for this. Pardon?
the paired one? The
Yeah, it's not.
And also for the it's quite impressive if you need a few steps for two cosmological parameters. But how does that scale? How do you expect it to scale with more?
Oh yeah, so like H naught and all like.
Yeah, you have more.
I don't think so. Like so, as long as I can get the pretty accurate I am actually testing this forecast using like few more parameters like omega matter and the H naught and so on, and as long as I get pretty accurate numerical gradients, as long as it's not very noisy, then the number of steps do not increase drastically.
Okay, Zach.
So this work is all on simulations as well, right? Just going back to the Aaron paper that gave the model you're using, he, I think, found like 7.2% chance on that sigma 8, unless I'm misreading that. So it seems consistent with what you're doing, but why didn't you do much better if you've added all these additional modeling details, or is this more robust? And what's the
I mean, like, I think the 7% you're referring is with the AP, the free, and with the AP fixed, then the constraint gets much tighter in this case.
I think the 7% is fixed. But like, what is the additional stuff beyond the Aaron model here?
Not really. So we have like things I did differently than the what's shown in this paper is getting like better the calibration term for this from the simulation. That's one thing. For for like velocity dispersion terms, and I use the tighter like the priors on them. That's one thing, and I also use like the different optimization algorithm, but I don't think they'll make any much difference on this.
The optimization algorithm is not much faster.
It is faster, but I don't think it's gonna affect the constraints too much.
There's no further questions. Thank all the speakers again. We can break the meeting.
And then back at 1:30. Is that right? Yeah, 1:30.
Everyone, lunch will be on the 3rd floor, and please come back by 1:30 for the afternoon session.
Thanks for the recording.
Yeah, hope it worked.